In this video, I'd like to work out for you an example of a problem involving conservation of momentum. The problem is exercise 10 from the end of chapter 7. Why don't you take a minute and read through the problem to become familiar with the situation and the numbers, and then turn the video back on and follow along for a solution along with a discussion of some of the main ideas of the idea of conservation of momentum. Plus, I'll do one small extension for this problem that's not written in what's in the book. So the problem is about two football players that are running toward one another, one running north, the other running south, and they collide and stick together. So I made a little sketch over in the corner there where one of the runners, one of the football players, has a mass of 108 kilograms and is moving north, so I chose north to be up, at 3.2 meters per second. And the other football player, smaller, has a mass of 79 kilograms and is initially running south at 5.6 meters per second, so a little bit faster. And I do want to emphasize that all of this is happening on a number line or a coordinate system. And because momentum is a vector, we're going to have to have a way of incorporating direction for vector quantities like velocity and momentum. So I'm going to draw a little arrow to remind myself that north is in the upward direction on my diagram, but I'm going to assign north to be the plus direction. So anything that comes out minus will mean that it's in the direction south. Or if I know something is moving to the south, and I want to incorporate that direction, then I'll have to use a minus sign for it. So the first part of the question asks us to calculate the initial momentum of each of the football players. So that's a pretty straightforward thing. Momentum is equal to mass times velocity. So if you want to find the momentum of the first football player, you take the football player's mass, multiply by his velocity. So you're going to have 108 times 3.2 meters per second, and I get 346. And the units for momentum are just kilograms for mass times meter per second. There's no special unit. Now, one thing that's worthwhile noting, since momentum is a vector, we have to assign it a direction. So in words, I would say that that's north. However, if I want to do math on this, I would just use a plus sign to indicate that as a northerly direction. So in words, you say directions in words. Mathematically, you can assign signs. All right, so what do you get for the momentum of the second football player? M2 V2, you got to plug in his mass, 79 kilograms, his velocity, 5.6 meters per second. And if you multiply those together, you end up with 442 kilograms times meters per second. But it's important in words to note that that's south because the momentum of the second football player is in the southerly direction since he's running south. Or in numbers, I would just remember to incorporate a minus sign for that momentum. So that part's not too hard. Now, the next part of the question asks us for the total momentum of the system. So if I want the total momentum of the system, then I add these up. And the way to add something that's north to something that's south is by using plus and minus signs. So momentum of the first player is to the north, momentum of the second player is to the south, minus. So instead of adding these things, ultimately you end up subtracting them. And you end up with a total momentum before the collision equal to minus 96 in SI units, kilogram meter per second. And what's the meaning of that minus sign there? Well, if you had to say it in words, you have to note that the total momentum is south. So you would never say in words or write a sentence to say the total momentum is minus 96 kilograms meters per second, because you don't use plus and minus signs in words. That's only a mathematical trick. The last part of the question asks rather abruptly, if afterwards they're stuck together, how fast will they be moving? So after the collision, the situation looks a tiny little bit different. They're both stuck together to make one common mass, and they're moving in some direction, v, but the speed is the same for the two because they're stuck together. Now we have a hint as to which way, after the players are stuck together, they'll be moving, because conservation of momentum tells us that the total momentum afterwards, I'll use a prime for after, has to equal the total momentum before. So no prime before, prime after. So this is the statement of conservation of linear momentum. When there are no external forces, or if there are external forces but the collision happens really fast, and there's no time for those forces to deliver any impulse to the system, then momentum can't change. So final equals initial. So the reason why this is a clue as to which way the players will be going after the collision is because their momentum has to continue to be the same. It has to be moving to the south. So their final velocity, their final speed, I should say, is got to be directed to the south, but we don't really know how fast. Except to say that the final momentum is the product of the combined masses times the velocity. So to get to the answer of the problem, we would simply say that the total momentum afterwards has to equal minus 96. I'll leave off the units for now. And that has to equal the sum of their masses, because they're moving together at some common speed. So prime means after. So you can solve this little equation here for what their speed is afterwards. You just have to divide 96 by the sum of their two masses. So the speed the two players are moving after the collision is 96, that's their momentum, divided by the sum of their masses because they're stuck together. And if you do that, you end up with minus 0.51, according to my calculations. And then the kilograms would divide out and leave you with meters per second. So what's the meaning of this minus sign again, to reiterate? It means that they're both moving together to the south. So that concludes the problem that the book wanted us to figure out, but I would like to add a little bit more here. What I'd like to add is an exploration of how the momentum of each of the players individually changed as a result of this impact. So I want you to remember a few things. That player 1 beforehand had a momentum of 346 kilogram meter per second, and player 2 had an initial momentum of 442 kilogram meter per second to the south. And that their total momentum came out to be 96. So why don't you make a record of those numbers, because I'm going to erase part of this and try something new. Specifically, what I would like to try to calculate here is how much did the momentum of each player change. So I'd like to calculate the change in momentum for player 1. Or if I wanted to come up with a symbol like for that, I would like to calculate delta P for player 1, which, by the way, is calculated in the usual way. The momentum of player 1 afterwards minus the momentum of player 1 beforehand. We already have what the beforehand is. It's 346 directed to the north. We need to calculate the momentum of the player after they're stuck together. So even though the two players are stuck together, each player has a little bit of momentum individually. And if you wanted to find or calculate the momentum that player 1 has after the collision, you would have to take that player's mass and multiply it by that player's velocity. And you would subtract from that what that was before. But I want you to know that here you're not going to use the momentum, the mass of both players together, because we're asked only to find the change in momentum of one player. So if you plug some numbers into this, let's see what you get. According to my calculations, afterwards, minus 55 kilogram meter per second. And beforehand, it was 346 kilogram meter per second. So what do you get if you subtract those? I get maybe around 400, 401. Do it on your calculator and tell me what you get. By the way, notice that you got the minus sign here. Let's not forget why that's there. It's because this momentum is to the south. So you got to remember to hit that with a minus sign. Anyways, I think you get something on the order of minus 400 kilogram meter per second. I rounded off a little bit there. Rounded off 1 to make it a nice easy number. What if you wanted to calculate the change in momentum of player 2, for example? Well, that would be momentum of player 2 afterwards minus the momentum of player 2 before. And before, the momentum of the player was 442, but directed to the south. So if I plug in some numbers here, I end up with something that looks like this. Minus 40 kilogram meter per second. That's what you get if you take the mass of player 2, 79 kilograms, and multiply it by player 2's velocity after they're stuck together. That's 0.51 meters per second, but it's directed to the south. So you got to make it minus. And then you got to do minus, but the momentum of player 2 initially was itself to the south. So you have to include that minus sign. So minus 442 kilogram meter per second. So what's the change in momentum of player 2? Well, looks like it's minus 40, 2 minuses make a plus 442 is equal to plus 400 kilogram meter per second. This is an extremely important observation to make note of, and that is that the change in momentum of player 2 and the change in momentum of player 1 are equal to one another, except they're oppositely directed. So player 1's momentum was changed by 400 kilogram meters per second to the south, whereas player 2's momentum was changed by the same amount but to the north. In other words, the change in momentum of player 2 is equal and opposite to the change in momentum of player 1. But that's not an accident. That's a consequence of Newton's third law, because the forces that each of the players exert on one another are the same. So their change in momentum are the same because the collision took the same amount of time for each one of them. Or, said another way, the total change in momentum is 0. So whatever momentum, let's say, player 2 gains, player 1 has to lose. So that's why the change in momentum of the two players are equal to one another. And I'd like to try one last thing. I'd like to estimate how big the forces are exerted on player 1 by player 2 and vice versa. So that really won't be too hard because we can use the impulse momentum theorem to calculate that. So for example, we know that the momentum changes if an external force is exerted. So In the case of this thing so far, we've considered mass 1, player 1, and player 2 to be a single entity, a single system. And since there were no external forces, then the momentum before and the momentum after are equal. But we can change our point of view and focus in on a single one of the players. Let's say player 1. We can figure out, if we draw an imaginary box around player 1 using the change in momentum of player 1, what force must have been exerted on player 1. That's because of the impulse momentum theorem. So the change in momentum of player 1 has to be equal to the net force exerted on player 1 times the time that force was exerted. Well, what's exerting a force on player 1? Well, the answer is player 2. So this force really is the force exerted on player 1 by player 2. Let's see if we can figure out what that force is. But in order to do that, we're going to have to estimate how long it takes the two football players to come in contact with one another and then end with this common final velocity. I don't know what to say about that. Let's just say it's half a second. So that would mean from the time one player first touches the other player to the time they're all tangled up getting ready to be tackled to the ground, it's a very short interval of time, say half a second. So if we estimate that, we can find the force exerted on player 1 by player 2 by dividing the change in momentum of player 1 by the time this force was exerted. So we had said that that was around 400 kilogram meter per second for the change in momentum of player 1, and the time interval we're estimating to be half a second. To be fair, the change in momentum of player 1 we found to be negative because it's directed to the south. Player 1 was initially moving north, but finally moving south, so player 1's momentum got changed to the south, minus. In any case, when you do this, you find that the force that is exerted on player 1 by player 2 is around minus 800 newtons. And what's the point of this minus sign? Same as ever, means to the south. So when these two players collided, player 2 exerted a force on player 1 that was directed to the south. And it's equal to 800 newtons. Now what about the force exerted on player 2 by player 1? Well, I think you realize now this is an action-reaction force pair, so it has to be equal to 800 newtons, but in the other direction, north. And if you were to go through the calculation, which would be unnecessary really to show it, you realize you'd have exactly the same numbers here, except the change in momentum of player 2 wasn't minus, it was plus, because it was directed to the north. Because player 2 was initially moving to the south, but then ended up moving to the south more slowly. So player 2's momentum got changed to the north. In any case, that's a pretty complete discussion of exercise 10 in chapter 7, with an additional part to figure out the change in momentum of each of the players, and use that along with the impulse momentum theorem to calculate the force each player exerts on the other.